Hi everyone, this video is prepared for our first subtopic in topic 3, the basis and dimension of a vector space. So let's go to the definitions of a basis for a vector space. To define basis, we firstly have a vector space V. So we denote V as a vector space, and then we have another set S. S is a collection of some vectors in V. Therefore, V1, V2, up to Vn are all vectors in the vector space V. This set S is called a basis for the vector space V if it satisfies two conditions. The first condition is S should be a linearly independent set. Recall that S is linearly independent if and only if K1, K2, up to Kn are all 0, are the only solution, the only scalars, such that K1 V1 plus K2 V2 plus up to Kn Vn equal to the 0 vector in V. Okay, you have to be careful that this zero vector is not necessarily 0. It's in fact a 0 vector in V. Alright, so that's the first condition. The second condition is S spans V. Recall from the second subtopic in topic 3, S spans V means span V is equal to span S is equal to the vector space V. So this is equal, that means there are two things. The first thing is span S is a subset of V and V is a subset of span S. The first property, span S is a subset of V, is obvious. Obvious because every element in S are vectors in V, and V itself is a vector space. Therefore, any linear combination of vectors in S is an element in V. So one is obvious. So to show that S spans V, it is sufficient that we show that V is a subset of span S. Okay. So to show that V is a subset of span of S, we have to show that for every vector space V in V, there exists scalars. Let's say we denote as K1, K2 up to Kn, such that the vector V is K1 V1 plus K2 V2 plus up to Kn Vn. Why do we have to show this? That is because this is an element of span S, because span S is a collection of all linear combination of vectors in S. So let us start with a very simple example on R3. Okay, the vector space here is R3, and the subset of R3 that we are considering here is a set of three vectors I, J and K, where this is I, this is J, and this is K. So we have to show that this set S is a basis for R3. Recall from the previous definition, S is a basis for R3 if S satisfies two conditions. The first condition is linearly independent. The set S here should be linearly independent. As we have seen in example 3.15 in the previous subtopic, we have shown that this set is linearly independent in R3. So what's left? What's left is we have to show that span S, so this is S, is equal to R3. To do that, we have to show that, span S is equal to R3, we have to show that every X in R3, X is a linear combination of I, J, and K. Okay, so we have to show that there exist colors K1, K2, and K3 such that S is equal to this term. Okay, so to do that, we start by letting a vectors in R3. So we let V as a vector in R3. In my explanation, I have used X instead of V, but doesn't matter, it's just a symbol. Okay, so here let's V be an element in R3. We aim to show that V is a linear combination of I, J, and K. It is obvious that for an arbitrary vector V is with the first component V1, second component V2, and third component V3. So we have seen here, you can see here that the vector V is a linear combination of I, J, and K, where the scalars K1, K2, and K3 are V1, V2, and V3 respectively. Therefore, the vector V is an element in the span I, J, K, and therefore the set I, J, and K span the vector space R3. Okay, and we have shown that the set I, J, and K satisfies the two conditions to form a basis for R3. In this example, we are still considering R3 as a vector space, and the set S is a set of V1, V2, and V3, subset of R3, where V1 is here, V2 is given here, V3 is given here. Alright, so here again we have to show that S is a basis for R3, and therefore we have to show that S satisfies two conditions. The first condition is S should be linearly independent set. Alright, so to do that, we write this equation. Okay, we write this equation where V1 here is from the set S, V2, and V3. And the scalars C1, C2, and C3 are scalars that we are looking for. We have to find the scalars C1, C2, and C3. And 0 vectors here is the 0 vector in R3, which is 0, 0, 0 as the 0 vector in R3. Okay. Remember, we have to find the values of the scalars C1, C2, and C3. To do that, we substitute the value of V1, V2, and V3 here, and the 0 vector. Therefore, we have this. We do the operations on the left side, and then we have this. To find the value of C1, C2, and C3, we are going to compare each component in both sides of this equation. So this is first component, the second component, and the third component. Okay, then by considering both sides of the equation, component by component, we end up to a systems of linear equation with variables C1, C2, and C3. Remember, our aim in this proving is to find the values of C1, C2, and C3, because we want to answer questions. Is 0, 0, 0 are the only solutions for C1, C2, C3, or do we have some other values or some other solutions for C1, C2, and C3? So to do that, we get the coefficient matrix for the systems of linear equation, okay, as given by the matrix A in the slide, and then we get the determinant. We find the determinant of the coefficient matrix, and we found that the determinant of the matrix A is not equal to 0. And by lemma 2.8, you may refer to this lemma. Since the determinant of A is not equal to 0, then A is invertible, right? And then by theorem 1.3, since the coefficient matrix A is invertible, therefore this systems of linear equation has only trivial solution. Okay, this systems of linear equation has only trivial solution. Trivial solutions means C1 equal to C2 equal to C3 are all zeros. Okay, there are no other solution for C1, C2, and C3. They are all only 0, right? So since we don't have any other solution for C1, C2, and C3, therefore the set S with 3 vectors V1, V2, and V3 is linearly independent. Okay, to complete the proof of S being a basis for R3, in the second part, we have to show that span S is equal to R3, where S is the set S here is a set of V1, V2, and V3 as given in the question. Recall that to show that S span the vector space R3, we have to show that for every vector in R3, B is, okay, the vector V is in span S. Okay, to show that B is in span S, we have to show that B is a linear combination. Pardon my writing. B is a linear combination of S. And to show that B is a linear combination of S, we have to show that we may write B as K1 V1 plus K2 V2 plus K3 V3 for some scalars. K1, K1, K2, and K3. That's mean we are able, we can find the values of K1, K2, K3 such that we may write B as this equation. Right. So this is what we are going to show in this part. Alright, so we start our proof by let B be any vector in R3, where B is a three tuple with components B1, B2, and B3. Okay, therefore B1, B2, B3 are all scalars or are reals. Okay, and then remember that we have to check that B is in element of span S, where S is a collection of V1, V2, and V3. Okay, so we let B as C1, V1 plus C2, V2 plus C3, V3. Okay, so we substitute V1, V2, V3 because we want to find the scalar C1, C2, and C3. Alright, and then we have this by doing the arithmetic operation. Alright, and then we're comparing left and right side of this equation, component by component. Okay, and then again we end up to a system of linear equation. We end up to a linear systems of linear equation. Bear in mind that we are finding the values of C1, C2, and C3. Alright, so to find the value of C1, C2, and C3, we have to solve the system of linear equation by using any method. We compute the determinant of the matrix A, where matrix A is the coefficient matrix of the systems of linear equation, and we found that the determinant of A is non-zero, and therefore by lemma 2.8 the matrix A is invertible, and therefore by theorem 1.3 the system of linear equation, okay, this is system of linear equation that we have produced in the previous steps. The systems of linear equation has only unique solution. That means the solution exists, and therefore the scalars C1, C2, and C3 exist. So B is a linear combination of V1, V2, and V3, and therefore B is in the element of span V1, V2, and V3. Therefore, we have shown that R3 is equal to the span V1, V2, and V3, and therefore V1, V2, V3 satisfies the two conditions to form a basis for R3. From the previous example, we have seen that there are two sets which form a basis for R3. Okay, therefore, basis for a vector space is not unique. Okay, so whenever we have a vector space V, we may found different basis for the vector space V. It is very important to identify the standard basis for a vector space. Okay, and the standard basis for a vector space should be unique. For an example, in Euclidean n space, Euclidean space for n-dimensional Rn, the standard basis for this vector space is a set of n vectors. A set of n vectors. Here, we denote as E1, E2 up to En, where E1 is this, where the first component is 1 and the rest are zeros. In E2, the second component is 1 and the rest are zeros. And En is whenever the last component is 1 and the other components are 0. Okay, whenever n is equal to 2, we have R2, two-dimensional Euclidean space, and the standard basis for R2 is E1 and E2, where E1 is I and E2 is J. Okay, instead of use E1 and E2, we denote this as I and J. In a three-dimensional Euclidean space, R3, the basis is a set of E1, E2, and E3. So this is E1, this is E2, and this is E3. E1 we denote as I, E2 we denote as J, and E3 we denote as K. Okay, whenever n is greater than 3, we use E1, E2 up to En instead of I, J, and K. In example 3.30, the vector space here is Pn. So this is the vector space. Pn is a collection of all polynomials of degree n, where the element of Pn is polynomial Px given by A0 plus A1x plus A2x squared plus 2 An x to the power of n. And the set of vectors in Pn, which is the set S, is a collection of n plus 1 vectors. Collection of n plus 1 vectors, or the collection of n plus 1 polynomials, where the first polynomial is 1, the second polynomial is x, up to n plus 1 polynomial, which is x to the power of n. So, is this set S form a basis for Pn? Yes, because you may refer to example 3.24 that this set S is linearly independent. Okay, and then in example 3.18, we have shown that span S is equal to the vector space Pn, and therefore S is a basis for Pn. And in fact, this set S is regarded as the standard basis for the polynomial Pn. In this example, the vector space V is a collection of all 2 times 2 matrices, and the set S is the subset of the vector space, which consists of 4 matrices, M1, M2, M3, and M4. We have to show that the set S here is a basis for this vector space. To do that, in the first step, we have to show that the set S with M1, M2, M3, and M4 matrices is a linearly independent set. To show that this set is linearly independent, we have to consider this equation. Okay, where M1, M2, M3, M4 are in S, and C1, C2, C3, and C4 are scalars that we have to verify its values, and 0 vector here is the zero vector in matrices, which is a matrix with zero entries. Alright, so now we are going to verify the value of C1, C2, C3, and C4. We have to show that the set is linearly independent, we have to show that the only possible value of C1, C2, C3, and C4 are all zeros. Alright, so to get the value of the scalars C1 up to C4, we substitute the matrices M1 to M4 and the zero vector. And then we have this. Okay, and then we do the arithmetic operations. We end up to this equation. And after that, we compare each entry on both sides of this equation. And we have found that all scalars C1, C2, C3, and C4 are all 0. Therefore, this set is a linearly independent set. In the second step of the proving, we have to show that span S is equal to the matrix space. Equal to the vector space. Whereas here is the set of M1, M2, M3, and M4. And again, to show that these two sets are equal, we have to show that for every matrix in the vector space, A is an element of span S. To do that, we have to show that A is a linear combination of M1, M2, M3, and M4. That means we have to show that the scalars C1, C2, C3, and C4 are all exist such that this equation is true. Alright, so to do that, we let A be any matrix in the vector space, where A is a matrix of entries A, B, C, and D. Alright, so to show this equation, we start by writing the equation, and then we have to find the values of C1, C2, C3, and C4. Okay, so to do that, we substitute the values of the matrices M1 up to M4. Okay, we do the operations. We end up to this equation of matrices, and then we compare every component. Component 1, component 2, component 3, and component 4. And then we have found that C1 is A, C2 is B, C3 is C, and C4 is D. That means we can find the value of scalars C1, C2, C3, and C4 such that A is a linear combination of matrices M1, M2, M3, and M4. That means A is in span of set M1, M2, M3, M4, and therefore these two set is equal. And that complete the proof of the set S is a basis for the vector space of matrices of size 2 times 2. We have to note that the basis that we have shown for matrices of size 2.2 is regarded as the standard basis for this vector space. Right, so our first lemma, lemma 3.2. If we have a vector space V, okay, we have a vector space V and S, which consists of n vectors, v1, v2 up to vn, and S be a basis for the vector space V, then every vector in V can be expressed uniquely as a linear combination of all vectors in S. Alright, so let me repeat. If we have a vector space V, okay, and we have S, where S is a collection of vector V1, V2 up to Vn, and S is a basis for V. You have to bear in mind that basis is not necessarily a subspace. Basis is not necessarily a subspace of V. Right. So whenever S is a basis for V, then every time you pick a vector in V, every time you pick a vector in vector space V, this V is a linear combination of V1, V2 up to Vn. In other words, we may say that we may get V by a linear combination, or we may get V by using all vectors from the basis. And this is why a basis is very important for a vector space, because basis may represent the whole element in the vector space. To illustrate the theorem 3.2, we refer to the example 3.29, that a set of three vectors V1, V2 and V3 is a basis for R3. And therefore, from theorem 3.2, for any vector in R3, let's say vector X, X is expressible uniquely as a linear combination of V1, V2 and V3. That means we can guarantee that the scalars C1, C2 and C3 exist and they are unique. To show this, we may check to show this. So this is just an example. Let's say X is 1 to 3. X is 1 to 3. And what are the value of C1, C2 and C3? So to get the value of C1, C2 and C3, we simply substitute the vector X and the vector V1, V2 and V3. And then we end up to a system of linear equation. To find the value of C1, C2 and C3, we have to solve the systems of linear equation by using any method. And we found that the value is C1, C2 and C3, and the value of C1, C2, C3 are here, and this value is unique. Okay, therefore 1 to 3 is expressible uniquely as a linear combination of V1, V2 and V3. The theorem 3.9 is very important because we might want to use this theorem, for example, to form a basis for a vector space later on in some examples. Alright, so the contents of this theorem: we have a vector space V, and S, which has n elements of vectors in V. S has n vectors in V, is a basis for V. S with n vectors is a basis for V, and then we have a subset of V, S prime. So we have a subset of V, S prime, and note here that S prime is not necessarily a basis and not necessarily a subspace of V. Okay, the first content of this theorem. If S prime has more than n vectors, S prime has more than n vectors, then S prime is linearly independent. Okay. If the number of elements in S prime is more than the number of elements in a basis for V, then S prime definitely a linearly dependent set. Alright, and then if S prime has fewer number of elements, that means fewer than n, then it does not span V. Okay, let me repeat. If the number of elements in S prime is less than the number of elements in the basis of V, then S prime does not span V. Okay, then I left the proof for you to read and try to understand. Step by step is given in this slide and the next slide. Next theorem, we have a vector space V, okay, and then we know that basis for V is not unique. Let's say we have S1 and S2, both are basis for V, because we know that basis is not unique. So this theorem says that the cardinality of every basis is equal. The cardinality of a set which form a basis for V is equal. So if S1 has n number of elements, then S2 also has n number of elements. The proof for this theorem is by using Theorem 3.9. You might want to try to prove this. Alright. It is important to identify the number of vectors in basis for a vector space. Okay, why? We are going to see that in the next slide. Okay, in this slide, we are going to see the term dimension of a vector space. The dimension of a vector space. Okay, so let's say we have a vector space V. We have a vector space V, and basis for V has a finite number of elements. Basis for V has a finite number of elements. And then we define the dimension of the vector space V as the number of vectors in a basis, and we denote as dim V. Okay, so therefore dim V is the cardinality of S, where S is a basis for the vector space V. Alright, for example, zero vector space. Remember that for any vector space V, let 0 be the zero vector of a vector space, and a set of a singleton set with the only element is the zero vector is a zero space, is a zero vector space. We have seen that in the previous topics, in the first subtopic of topic 3. And we note that the basis for this the basis for the zero vector space is empty, and therefore the dimension of the zero vector space is 0. It has 0 dimension. Okay, another example. Okay, finite dimension vector space. Finite dimension vector space is whenever whenever the vector space has basis with finite element. Okay, finite dimension vector space is a vector space with a finite elements in its basis. For example, Rn, n Euclidean space, polynomial of degree n, matrices of size m times n. Alright, and these 3 examples are vector space with infinite dimension of vector space. Why? Because its basis, the cardinality of its basis is not finite. Okay, for Pn, where Pn is a collection of all polynomials of degree n, we have seen that this set is the standard basis for Pn, and this set has n plus 1 vectors. This set has n plus 1 vectors, therefore the dimension of Pn is n plus 1. And matrices of size m times n, we have right. Previously we have seen that for matrices of size 2 times 2, the standard basis consists of m1, m2, m3, and 4. Okay, where these are 2 times 2 matrices with single entry of 0, and the rest entry are all zeros. So for m2 times 2, we have 4 kind of matrices of this kind, and this collection form a basis for m2 times 2. Therefore, the dimension for m2 times 2 is 2 times 2 equal to 4. You may generalize this to see that for matrix of size m times n, matrix of size m times n, the standard basis for this vector space has m times n matrices with single entry of 0 anywhere in the matrix entries, and the rest are 0. And therefore, the dimension of matrices of size m times n is m times n. Example 3.32, determine the basis and dimension of solution space of the following systems of linear equation. Right, so we are given systems of linear equation where the scalars on the right side of each equations are all 0. Therefore, this system is homogeneous system of linear equation. And we know that every homogeneous systems of linear equation have solution where it is either unique or infinitely many. Right, so every homogeneous systems of linear equation has solution which either unique solution, which is the trivial solution, or it has infinitely many solution. Doesn't matter which case is, but the solution exists for the previous systems of linear equation. Let's say we collect all of the solutions of the systems of linear equation in the set S. So we might write the set S as A1, 5 tuple, in R5. Why does it has 5 elements? Because we have 5 variables. We have 5 unknowns in the previous systems of linear equation. So each value here is the value for the variable. So this one for x4, this one for x5, etc. All right. So alright, so we write the set S where AI, A1, A2, A3, A4 and A5 satisfy all equation. In the system of linear equation. Means that whenever we substitute x1 with a1, x2 with a2 up to x5 with a5, then all the equations are satisfied. Alright, so we have seen here the set of solution of the systems of linear equation is a subset of R5. If we equip the set S with the standard addition and scalar multiplication, then you might want to check that the set S is a subspace of R5, and S is a vector space. So S together with plus and scalar multiplication, addition and scalar multiplication, the usual scalar on R5 form a vector space. Therefore, since S is a vector space, we should be able to identify its dimension and its basis. That's what we are going to do in the next step in this example. Alright, therefore the set of all solutions of the homogeneous systems of linear equation in the previous slide is a vector space, and we call it as a solution space of the systems of linear equation. To determine its basis and dimension, as asked by the question, we are going to solve the systems of linear equation first by either using a Gauss-Jordan elimination or Gaussian elimination. Right. So to do that, we have to determine the augmented matrix of the system, and it is given in the slide. And then we perform the elementary row operations to reduce to row echelon form. All right. So, and next step, we are going to solve the systems of linear equation by using the reduced row echelon form, and we will get the corresponding systems of linear equation from this reduced row echelon form. Before that, we have to note that variable x1, x3, and x3 and x4, these are leading variable because each of this column contains a leading one. And okay, so leading variables are x1, x3, and x4, and the rest x2 and x5 are free variable. If you don't remember how to determine which variables are leading variable and which variables are free variable, you have to refer to topic 1 on solving systems of linear equation by using Gauss-Jordan elimination and Gaussian elimination. Okay, so here is the corresponding systems of linear equation from the reduced row echelon form of the augmented matrix, and then the leading variables are x1, x3, and x4, and free variables are x2 and x5. So we note that x2 and x5 are equal to two variables s and t respectively, and therefore we then write down the solution of the systems of linear equation in a set as follows. Okay, so from the previous step, we get this general solution as follows, and then we rewrite this general solution as an equation of column vector. Okay, so on the right side of this equation, the entry have two parameters s and t. So on the right side, we rewrite it as an addition of another two column vectors as follows, where the first column vector contains only parameter s, and the other column vector contains only parameter t. Okay, and from here we will get the dimension, basis and dimensions of the solution space. Okay, to do that, in here what we did is we bring s and t to here. We factorize s and t, and therefore we have a column vector here. These two column vector without parameter s and t form a basis for the solution space, right? So these two vector that we take from here form a basis for the solution space. Okay, so in the previous step, we have we got two vectors. We denote it as v1 and v2. Both are subset of 5 Euclidean vector space. And later, what we are going to do is we are going to prove that S is a basis for solution space. Okay. Okay. So as you might check that this set S is a basis for solution space of the systems of linear equation, because the set S is linearly independent and span the solution set of the systems of linear equation. Okay, therefore, the basis of the solution space is a set with two elements, where the first two vectors, where the first vector is v1 and the second vector is v2. And therefore, the dimension of the solution space is 2 because we have 2 elements in the basis of the solution space of the systems of linear equation. Theorem 3.11. We have a vector space V where V is an n-dimensional vector space, which means that the basis for V must has n vectors. Okay, and then we have another subset of V. We denote S as the set S. The set S is subset of V with n vectors. So S has n elements in it. Alright. The first content of this theorem says that if S spans V, then S forms a basis for V. Alright. So to show that S forms a basis for V, we have to prove that S spans V. Okay, that's mean here. V is a span of S. Okay, so in the second contents of this theorem, it says that if S is linearly independent, then S forms a basis for V. Alright, so in the second contents, it says that to show that S forms a basis for V, then we only have to show that S is linearly independent set. So if we have a set with n vectors, then this theorem will help us to prove that S is a basis for V by either show that S spans V, or we have to show that S is linearly independent. In this example, we are considering two equivalent vector space. And we are given two vectors v1 and v2, and we have to show that the set S with v1 and v2 is a basis for R2. We are going to show this by using the help of the previous theorem. Why do we are able to use the previous theorem? That is because the dimension of this vector space is 2. We know that the dimension of R2 is 2, and the set S has only 2 vectors. Alright, the set S has only 2 vectors. So here n is equal to 2, and the set S has 2 vectors. Alright, so by using the help of the previous theorem, to show that this set that I have been called a set S is a basis for R2, by either show that the set is span the space R2, or we have to show that the set S is linearly independent. Right? Let's say we decide to show that the set spans R. Okay, so we are going to show that the set S spans R2. So we are going to show that R2 is equal to span V1 and V2, where this set is the set that I have been called as the set S. Right. Recall that to show this, we have to show that every element in R2, every vector space in R2 is a linear combination of V1 and V2. So we start our proof by we let x1, x2 are element in R2, and then we write x1, x2 as a linear combination of v1 and v2. Okay, so we assume that this vector is a linear combination of v1 and v2. Okay, so we have this equation. We have to find the value of a and b. Okay, we want to verify if the scalars of a and b exist or not. Right? So after that, okay, by doing some operations on this equation and then comparing component 1 and component 2 in both sides of this equation, we end up to a systems of linear equation with two variables, with two unknown, and the unknowns are a and b. Okay, and then we try to solve this systems of linear equation. We look at the coefficient matrix of the systems of linear equation, which is denoted as the matrix A, as follows. Right. So next we determine the determinant of the coefficient matrix A. We found that the determinant is minus 50, which is non-zero, and therefore the matrix A is invertible. Therefore, from Theorem 1.3, the systems of linear equation has a solution. The systems of linear equation has solutions. We don't care what are the solutions, but we can guarantee that the scalars of A and B exist. Therefore, we have shown that every vector in R2 is expressible as a linear combination of V1 and V2. Therefore, the set S of V1 and V2 form a basis for R2. This example is similar to the previous example. The difference are we are given R3 instead of R2, and we are given a set of 3 vectors. Therefore, we are able to use the previous theorem and use similar arguments. Alright, by following the similar argument in the previous example, we determine the systems of linear equation, where the coefficient matrix of the systems of linear equation we form by looking at the vectors v1, v2, and v3 in S, where the first column is the first vector, second column the second vector, and the third column of the matrix is the third vector. Okay, then we determine the determinant. We get a non-zero value, which means that the systems of linear equation has solution, and therefore every element in R3 is expressible as a linear combination of V1, V2, and V3. Therefore, the set with V1, V2, V3 form a basis for R3. In the previous examples, we considering S a subset of R2, and also we are looking at another set S in R3. And from the previous examples, we are able to generalize steps to prove that a set S in Rn as a basis for Rn. Okay, in general form of a set S in Rn, okay, we need n vectors. So here we have n vectors, u1, u2 up to un. we have n vectors to form a set. Okay, and this set is the set S. To show that this set S is a basis for Rn, we then determine the coefficient matrix, where the coefficient matrix we get it from vectors in S. Okay, so here is vector 1, U1. Here in the column 2, vector 2, second vector, U2, and up to n column. For the n column, it is from the n vectors, n vector, the vector Un. And then we compute the determinant. If the determinant is non-zero, then the set S is a basis for Rn. This is the last theorem that we are going to look at in this fourth subsection, where this theorem will help us to form a basis for a vector space V. Alright, we are going to see later on that this theorem will help us to construct a basis for a vector space V. Okay, so the contents of the theorem, we assume that S be a set of finite vectors of a finite dimensional vector space V. So we have a vector space V where the dimension of V is finite. Okay, therefore V is a finite dimensional vector space. And then we have a set S. Okay, we have a set S which is a subset of V, and S contains finitely many elements. S contains finitely many vectors in V. Alright, so the first contents of this theorem says that if S spans V, but S is not a basis for V, then we may reduce S to form a basis for V by removing some vectors from S. Okay, so if S spans V, but S not yet a basis for V, then we might construct a basis for V by using S. How? We may remove some vectors in S until what's left is vectors that form a basis for S. Okay, and in the second part, second contents of this theorem, it says that if S is linearly independent but not yet a basis for V, then we may construct a basis for V by enlarge the set V. That means we insert some vectors into S until it's form a basis for a set for the vector space V. In this example, we are considering a polynomial of degree 3. Okay, we know that the dimension of P3 is 3 plus 4. Sorry, please, 3 plus 1, which is 4. And we have a set S, subset of P3, and S contains a finite element, which is 2. So S has 2 elements, 2 vectors, right? And we know that since P3 is has dimension 4, then the basis for P3 must contain 4 vectors. So S here is not yet basis for P3 because every basis for P3 must have 4 vectors, and the set S here is only has 2 vectors. Okay, therefore we are going to use the previous the previous theorem. Okay. Firstly, you need to check that the set S is linearly independent. You have to check that the set S is linearly independent. Since the set S is linearly independent, and then we are able to use the previous theorem. Okay, by using the previous theorem, we are going to add some vectors in S to perform a basis for P3. Okay, so what are the vectors that we are going to add into S? Those vectors are vectors in the standard basis of P3. Remember that the standard basis for P3 is 1, x, x2, and x3. Right? So there are 4 vectors in a standard basis, but here we only need another 2 vectors to be inserted into S. Why? Because S already has 2 vectors. So we need another 2 so that S will have 4 vectors to perform a basis. Okay. In between, among these 1x, x2, and x3, we're not yet sure which vectors should be inserted into S. So at the beginning, we add every vectors into the set S, right? So we have this set after we add every vectors in the standard basis, right? So firstly, we need to decide, do we need vector 1? Do we need 1? The answer is yes, because Y is not a linear combination of the first and the second vectors. Since 1 is not a linear combination of the first and the second vectors in S, so we need 1, because we cannot construct 1 from the first and the second vectors in S. Next, we have to decide, do we need X? We do similar steps, and we found out that we don't need the vector X, because we can get X. We can construct X by using the previous vectors. Alright, because X is simply minus 1 plus 1 plus X. Okay, this is a linear combination of the previous 3 vectors. So we don't need X. What about X2? It turned out that we also doesn't need X2, since X2 is a linear combination of the previous vectors. So we cross out X2. What left is X3. Okay, so since we need another 1 vectors, so X3 definitely will be inserted into the set S. So now the set S has 4 vectors in total, and you might want to check that this set form a basis for P3. Here is similar example to the previous one, but instead we have 4-dimensional Euclidean space. 4-dimensional Euclidean space, and we have the set S with 2 vectors. Okay, it has been given in this question that S is linearly independent. So we don't have to check if S is linearly independent or not. And we go straight to the theorem by using the theorem in the content in the second part of the theorem to show that to form a basis for R4, we need to add another 2 vectors in S. Okay, we follow the same argument by using a standard basis for R4. Okay, so the standard basis for R4 are E1, E2, E3, and E4. If you don't remember what are E1, E2, E3, and E4, you have to recall the basis topic. Alright, so we have to decide which among these 4 vectors that we have just insert, which vector should be we keep it in the set S, and which vectors should be excluded from the set S. Alright, by using the same argument, E1 is needed because E1 is not a linear combination of the previous vectors. Right, so what about E2, E3, and E4? E2 is not included in the, will not be included in the set S because E2 is a linear combination of the previous vectors. So do for E3. Okay, so what's left is E4. Since we need another one vector, so E3 will be included. Sorry, E4 will be included. So the set with 2 vectors included E1 and E4 form a basis for R4.